So now we are designing a singly reinforced RCC beam in which the span is given as say 4 meter and a UDL of 10 kN per meter is given, M20 Fe415. First of all, we have to decide the depth. Depth is decided as span by 20 as per page number given in page number 37, being simply supported is span by 20. It comes out to say 200, but now I am just making on the safer side 1/10 of that and say 400. Effective depth will be cover minus half the bar diameter 370. Generally, when we talk of the width of the beam, it is generally half of the depth, so it is 200. So our cross section will be 200 cross 400. Now, the UDL is given as 10 kN per meter, so maximum bending moment WL square by 8. It comes to 20 kilonewton meter. 20 kilonewton meter. FY2550, FY415 and FY500. Under three circumstances, we will have to calculate the value of some constants, and MUK max can be directly calculated as 0.149 FCKBD square. If it is 415, it is 0.138 FCK square, and if it is M500, it is 0.133 FCKBD square. Now you are using the second one, that is Fe415. Now we are designing a beam that is calculating the required depth, and that can be taken as FY415, FY415 and FCK20. Then MU max is equal to 0.138 FCKBD square. D required can be calculated, comes out to be found out to be how much it is, 190.34 mm. D required and D provided should always be compared, and we must see that D provided should always be less than, D provided should always be greater than D required. D provided is 370, required 190, it's okay. Now we have to calculate the area of steel, and that is to be provided. There are two mathematical expressions. One we call as the empirical mathematical formula, which is given over here, and another already given in IS code, page 96, which is given like this. So either of the two you can use this and find out the area of steel, in which FCK is 20, D is 370, B 200 and Fi is 415. MU max, it is to be converted into Newton mm, so multiplied by 10 to the power 6. Now substituting these values in one of the formulas so far, we are getting the value of area of steel as 156.67 mm square. Rounding it on the higher side is say 200 mm square. Providing 3 bars of 12 mm. Area provided is 3 into pi by 4 d square, 339 mm square, which should be greater than the required one. So it is that we can okay. But now here onwards, after these parameters have been calculated, now we have to apply the checks. First check is check for shear. Vu is equivalent by shear force is equal to WD LE by 2. WD is already given as 10, L is 4 and 2, it comes out to 20 kilonewton. Tau Vu, that is actual shear stress, is nothing but Vu upon BD, and it comes out to 0.27 Newton per mm square. Now shear stress taken by the concrete, which is called as tau C. From table number 19, page 73, the tau C can be calculated by first of all calculating the percentage of steel, that is PT, which is nothing but 100 AST upon BD. It comes out to be 0.44. Now table number 19, page number 73, tau C can be calculated by interpolation of M20 for PT as 0.45, and we found it comes out to be 0.456 Newton per mm square. 0.456 Newton per mm square. Now there are three cases for the tau v and tau c, so they check for this. One, when tau v is less than tau c and less than tau c max. Second, tau v is greater than tau c but less than tau c max. Similarly, third one is tau v is greater than tau c but still greater than tau c max. Now we'll deal one by one. First, considering the first case, that is when the actual shear stress is less than the shear taken by the concrete and also less than the maximum value of the tau c. Means the shear taken as the concrete is more and as per the actual concrete. Then at that stage, we'll have to provide the stirrups, and that can be taken from this mathematical expression given as ASB upon VSB, which is already given on page number 48. Where ASB is the area of the vertical stirrup, that it is two-legged or four-legged depending upon the number of vertical legs. We can, and considering the diameter area of steel for the vertical stirrup can be calculated. SV is nothing but the spacing of the vertical stirrup for the full length of the beam, and B is the width. Condition number 2, when tau v, the actual shear stress, is greater than tau c but less than tau c max. Here, so we'll have to provide the shear reinforcement. How to design the shear reinforcement can be very easily seen. First of all, calculate the balance shear force, that is Vu minus tau c Bd. That has already the formula is already given on page number 73 of IS code 456/2000. And for this balance shear force, find out the value of SV, that is Vu as the balance shear force, using this mathematical expression already given the same page. What we have to calculate is the value of SV. Case number 3, when tau v is greater than tau c and also exceeds tau c max. This is the maximum value of tau c max. This is also exceeding this one. Under such circumstances, no shear checks can be applied. Only what we have to do, you have to revise the section. You have to redesign the section. In our case, tau v is less than tau c and less than tau c max. So we have seen that tau v is 0.27 Newton per mm square. Tau c is 0.45, which is much more, and this is 2.8. Considering the second case, now we'll have to provide the two-legged 8 mm stirrups and calculate the area of steel of a vertical two-legged pi by 4 8 square 100.5 mm square. B is 200, Fy is 415, SV the spacing of the stirrups. When the spacing of the stirrups is known, then we can provide the stirrups in the longitudinal direction along the spacing that we have to calculate. Now ASV upon BSV, which is already given on page number 48, then find out the spacing of vertical stirrup and substituting value is getting out 453 mm center to center, but under any circumstances this spacing should not exceed 300 mm center to center. This is the maximum limit of providing the spacing. So we are providing two-legged 8 mm 5 vertical stirrup at the rate of 300 mm center to center throughout the length of the beam. Third check for the development length, LD. M1 upon B plus L0 should always be greater than the bond length, that is LD. This much length of the reinforcement is required for the proper bonding between the steel and the concrete, and this much is the length that we are already providing. So we must see that this provided length should always be greater than the required one. The formula is already given on page number 44. M1 is nothing but the maximum bending moment, V is nothing but it is 20, L0 is D or 12.5, whichever is more. It is already given over here, and LD is formula, this again formula given on page number 42. Substituting the value of phi as the diameter of the bar, tau BD. Now tau BD is the design bound stress from clause number 26.2 and page number 43. It has specifically mentioned in line number 2 that the deform bar, the tau BD should increase the value by 60%. Whatever the value of tau BD which is given in the table so far, it is to be increased by 60% if we are using the Tor steel, that is Fe415. So now we can see, first of all, M1 upon V. M1 is nothing but the moment, Mu max. V is nothing but the shear force. L0 is nothing but, there are the two conditions for L0. One, 12 times bar diameter or effective depth of the beam, whichever is more. So definitely 12 times bar meter 144, effective D 370, we are using 370 over. It comes out with 1370 mm. Substituting value of our LD for phi, this and everything, and we find that it comes out to be 564. Provided 1370, required 564. So we can say the bond is proper and it cannot be slipped from the concrete. The steel cannot be slipped from the concrete. Last check is the check for deflection. When beam deflects so far, under any circumstances, we have to see that the modification factor times span depth ratio, which is already given in on page number 38, figure number 4. Here we will have to find the value of modification factor based on the tau c. It comes out to be 1.4. So this is already given, and I think it is a page number. I have to confirm the page number. I don't remember so far page number for this. Maybe 38 or something. I don't know. Next number is there. I will see and I will let you know accordingly. It should be greater than actual span by actual depth ratio. So required is 22 and span by depth ratio 10. This is greater than this in OK. Now this is the final design of a beam having a span of 4 meter. Depth as 400 mm, width as 200 mm, 3 bars of 12 mm. This is the anchor bar and this spacing of 2-legged 8 mm phi at the rate of 300 mm center to center. These are the main bars, we can call 3 bars. This is an anchor bar. This is an anchor bar we can call as anchor bar, and which may be of 10 mm, 12 mm as per our sweet convenience. It can be, I am taking a say 10 mm bar. If I take it as 10 mm also, you can go for 12 mm, it makes no difference because it doesn't carry any load. It is just to anchor this stirrups over at the top. That's over and all about the design of an RCC beam when it is simply supported and it is loaded with a uniformly distributed load of WD, that is the design uniformly distributed load. If it had been given a working load, then it is to be multiplied by 1.5 to convert it into design load, and it will be taken as 1.5 times the working load, and that will give complete part of the design of this lab. Actually, in all the beam answers you have to see that minimum these 3 checks must be applied. That's over and all.